So welcome everyone to the last session of the day, which is the DeFi session. And to start off we have Weiye on quantifying the sub-optimality in routing for automated market makers.
Hello everyone, my name is Weiye, and today I'm going to talk about this joint work with Professor Ciamac, quantifying sub-optimality in routing for AMMs. This is an empirical audit on DEX routing. We investigate millions of swaps on Ethereum mainnet and constructed a reproducible optimal benchmark and use this to measure the inefficiency of realized on-chain swaps. We know that DEX aggregators rely on these smart routers to allocate flow across different pools for the best execution. So two questions rise naturally here. The first is, at a given on-chain snapshot, what is the optimal split across different pools? To be more specifically, how do we optimally choose the pools that we want to swap on? And how do we decide for what amount we want to send into these different pools? And the second question is, how close are these realized routes conducted by these routers to the optimal? So in this study, we fixed the input budget and trying to find the optimal allocation to achieve the maximum output from all these pools. So here, we characterize each pool by this output function at a given pool state and the swapping direction. The pool state omega j includes the current price and also the liquidity. For example, in the Uniswap V3 pools, since the liquidity is distributed across different ticks, so the pool state will also include the different liquidity within those different ticks. So here you can see from the graph that the amount of the two reserves will follow this constant product curve within each tick. So it will be piecewise concave, and since the marginal price wouldn't jump on the tick boundary, overall, this output function is increasing and concave function. And one thing to note that this output function is state-specific. Trades could change the price, and liquidity, adding or removing, could change the curve. So even if you planning earlier and execute later, you might be solving the right optimization problem, but using the wrong information and does not achieve as much as we want. In our study, we mostly focused on same pair routing. We have multiple pools, but with different transaction fees maybe, but all trade the same token pair, and we do not consider the routes via intermediate tokens. And so the question here is, why do we need to split those routes? Why don't we just pick the pool that has the lowest marginal price and put all of our input token into that pool? This is because we were going to have diminishing returns if we do so. Inputting more tokens into one pool will worsen the marginal execution. So this is why splitting helps. You can shift flow from a pool with worse marginal price to one with better marginal price, and thus will increase the total output. You can continue to do so until the marginal price equals across all these pools, and it achieves maximum output. So here's the mathematical formulation of this problem. This is a concave resource allocation problem, and solving it using KKT condition will give us exactly the marginal equalization condition I just explained intuitively. And for the algorithm, we write a code for this inverse marginal price function, which gives us the corresponding amount of input if we want to end up in a desired marginal price. And we use this inverse marginal price and also bisection to solve for this marginal equalization condition to get this first no-gas optimal benchmark. However, in reality, touching more pool is not for free. You need more gas to do so. So here's how we model in the gas. We're modeling the gas as a fixed activation cost if we're going to input positive amount of token into one pool. So here, the trade-off is that using more pools may improve the output, but each activated pools will add on this gas cost. And here is the mathematical form of this gas-aware routing. We assume that the gas is always paid in E's. So now the swapping direction Z not only determines how the output function looks like, but also determines whether we're going to put this gas cost in the objective or the budget constraint. So here, you can view this optimization problem as a two-layer structure. On the outer level, we're going to choose the active set S, which we're going to put a positive amount of input tokens into that. And in the inner level, we're just conditionally on using only these pools and solve inner concave problem the same way as we solved for the first benchmark. And since in our research scope, we only consider limited number of pools, so we can just enumerate feasible subsets of the pools and get the exact global solution, considering the presence of gas. So now we have the ways to compute an optimal benchmark. We can now measure the gap precisely. Despite there are already massive volume in AMM pools trading, there hasn't been a reproducible large-scale audit of how the realized routes nowadays are. And we're the first to account for both gas and the state. And the core idea here is we compute this optimal benchmark as specific state, and then compare each realized route on chain against this optimal. And this helps us to separate and investigate in two ways these realized routes could fail to perform good. One thing is missplitting. Conditional on these realized activated pool, maybe it's not split enough across different pools. And the second is underactivation, which means that maybe this realized routes just not consider enough pools or finding the more valuable pools to trade on. And we conduct our empirical analysis mostly around three questions. The first is, how large is this routing suboptimality and how is it distributed? And the second is, how do we quantify the value of this state information? And will the realized routes look more close to the optimal if we evaluate them at earlier, planning snapshots than actually in the execution time? And the third is, what is causing these extreme losses and huge suboptimality on certain trades? By solving the two optimization problem we introduced earlier, we're going to construct three benchmarks. The first is support constraint optimal, which we restricted to the only using the pools that realize the routes are using and consider there's no gas. And the second is full value optimal, which we allow to trade on all the pools that has this certain same pair swap. And the third is gas-aware full value optimal, which we allow all the pools and also consider this activation gas. So for example, let me give an example explaining how these three different optimal benchmark work in this analysis. For example, if the realized routes touches only pool 1 and pool 2, the support constraint optimal will ask, does it split optimally across these two pools? And full value optimal will ask, if there were no gas, should we add pool 3 and pool 4 into consideration and shift some of the flow onto those pools? And the gas-aware full value optimal will ask if there's if considering gas, are these extra pools still worth it to split those flows? For the empirical setup, we tested on almost 3 million ETH USDC swaps on Ethereum mainnet, which the total input amounts to about 120 billion. That means that even if the suboptimality is only a few basis points per trade, this could already aggregate to economically meaningful dollars. And we use the sub-optimality matrix defined as the output shortfall of the realized risk compared to a benchmark. And before we look into the comparison with the optimal benchmarks, we can first looking at this simple descriptive data analysis only on the realized routes. And it gives us an observation that the execution are highly concentrated. You can see that fewer than 1/3 of the pools on average are being activated per each transaction. And the flow shares are extremely uneven. Like mostly you just choose one of the pools and give all the input into it. And this may suggest a potential underactivation problem. Maybe we are not considering enough pools. And we are going to use our benchmarks to quantify this loss next. So here we are reporting in the graph the suboptimality between the realized routes to the 3 benchmarks evaluated at execution state. You can see across all the trades, the loss amount to about 6 million versus the support constraint optimal, and about 20 million versus the full value optimal and gas-aware full value optimal. You can see in the right graph, moving from support constraint optimal to full value optimal, the suboptimality increased a lot. Even if we add gas into consideration, it doesn't eliminate this suboptimality much. This suggests that one dominant gap is the missing activation of extra pools. The current routers just could split reasonably within the chosen pools, like comparison with the support constraint optimal. But they're activating 2 full pools, suggesting this large suboptimality compared with the full value optimal. And the second observation is that the suboptimality is heavy-tailed. We grouped the swaps into different trade size level. And in this graph, you can see no matter in which trade size level, the heavy tail phenomenon exists. The mean, which is the triangle, sit well above the medians and sometimes even above the upper quantile, suggesting that there is a small fraction of the trades that could account for much of the total loss and results in an extremely large suboptimality. And we would naturally think that there might be some time mismatching or sandwich attacks resulting in this, and we shall discuss later. We know that there's always been time discrepancy between the planning and the execution. No matter you're planning blocks ahead, clearly there will be transactions between these blocks moved state. Even if you are planning within the same block, the orders before you can shift the state. And as I mentioned earlier, the output function is state-specific. So if the state change, you may solve the right optimization problem, but on the outdated information and didn't get as much as you want. And next, we'll design some experiment and quantify this time stillness loss. So here we define omega 0 as the execution state and omega n as the state that is n blocks earlier. And we compute the optimal benchmark at omega n, which is using the outdated info and state, then compare it to the optimal benchmark, actually computed using the update info at execution time, and evaluate them both on the execution time. You can see that as the n increase in the right-hand side graph, there's a huge gap when n increase from 0 to 1, and the suboptimality continue to increase as n increase from 1 to 10. This suggests that even one block of staleness is already very large and cause a large performance drop. Additional delay keeps worsening the performance, but with diminishing increment. In the previous experiment, we are measuring the time staleness, but only comparing the optimal benchmark to each other. Here, we are comparing the realized routes against the optimal benchmark, computed as using earlier information and also evaluated at earlier blocks. Here, we wanted to find the answer to that, whether the realized routes align better with earlier snapshots, like the planning time, or with the actual execution time. You can see in the graph, as n moves from 0 to 1, there's a decrease in the sub-optimality gap, suggesting that evaluated on earlier snapshots, the realized routes looks closer to the optimal benchmark computed at earlier snapshots. And this suggesting that the current routers are making decisions based on a stale pre-execution information, in addition to mis-splitting and not activating enough pools. And previously, we mentioned that we have an observation that the sub-optimality have heavy tails. One hypothesis is that the heavy tail could be driven by the sandwich attacks. It's because these are rare events, but since it will move the state to an unfavorable direction, the conditional loss can be very large. We report the sub-optimality distribution on these three types of data set to see if we can find evidence of sandwiching attack causing heavy tails. The first row is the sub-optimality distribution on the full sample, and the second row is restricted to the data sample that was not sandwiched. And the third row are the data sample that was sandwiched. You can see, comparing the first row and the third row, the mean shortfall increased from like 4 basis points to about 40 basis points. This suggesting that sandwiching attacks is causing much larger sub-optimality compared to the full sample average. And by comparing row 1 and row 2, you can see the average, which is the triangle, sits more closer to the quantile box, consistent with less heavy tail phenomenon. These are all the evidence that could support that sandwich attacks might be one of the reasons causing these heavy tails in the suboptimality. Yeah, and these are all the results that we have from investigating the suboptimality in DEX routing. Thanks.
Thank you for the talk. If you have any questions, feel free to line up at the mics.
Hey there, nice talk. I'm wondering if you looked at networks that use non-sandwiching block builders like L2s such as Base or Arbitrum, and if that showed any difference in some of these extremes. I didn't actually catch which network you were looking at. I assume it was Ethereum?
Yeah, Ethereum net. We didn't look at other networks.
So questions related to the gas fee that you collected. Is the gas fee collected is the real data, or is actually how do you calculate the gas fee you being used in the model? The reason I'm trying to say is, and trying to understand that because technically if you pay higher gas, you could solve your time staleness because you become the first one to be mined in the block, and also potentially not delay. That's kind of change the execution of it. So you may not preventing, you may make the sandwich attack much expensive to attack. So I just want to get one thing to understand, have you done some research on using the gas fee as a way to have better execution? Second part, you sort of mentioned all the data has to be pre-execution. I was trying to understand there's no way you could get the data. All the data can get in all this router has to be pre-computed, the last block data. Because how would you get the data is not being mined in terms of execution that being used for the routing decision?
So for the first question, the gas cost we're having here is using what is suggested in the Tycho model, and it's basically just a gas estimation, not the real gas that is recorded by the on-chain data. And but even if we, as for the time staleness, even if we take into account this estimate gas cost, there's still a large gap when n goes from 0 to 1. I wouldn't say it's decreased a lot after we considering gas. And for the second question, we're doing this empirical audit pure offline. So by the time we assess these realized rules, we already have the information when they were executed.
Okay. Yeah. Another question is related to Roberto's. Like you right now, basically the model using data from Ethereum mainnet, which is 12 seconds. Now, if you move to like a base and whatever short, like 50 milliseconds, whatever block time, that's pretty super challenge for the router to refresh the snapshot, the latest, execution, the price, everything. If with that consideration in it, would that affect the execution quality potentially? And if so, like, I'm trying to get if that's changed from LP side, would that be adjusted to make this happen? Like, let's say a lot of people want to talk about V4, you can do dynamic feed, within a block. But if the block is so short, like, would actually dynamic feed be beneficial or not? Would that affect the decision of the routings? Because if there's no routing to the dynamic feed, they don't know what the dynamic feed looks like. They cannot estimate the pricing for the decision of splitting which pool you want to go to.
Yeah, I agree that the thing you suggest might be potentially true, but we haven't done like experiment using the data except for the Ethereum mainnet, so I can't give a sure answer to that.
Okay, all right, thank you.
Yeah, thank you. And could the next speaker go and set up?